Today's lesson is on the probability of events occurring together. The objectives of today's notes actually deal primarily with how a lot of formulas work. So pause the video, take a minute, read through the objectives and the important formulas, and then restart the video when you're ready for me to explain them after having read through them once yourself. To find the probability of an event, it's denoted as P of A is N of A over N of U. So N of A is the number of things that we want. N of U is the number of things in the universal set. So it's the part that we want out of the total number of things. Complementary events are denoted with the prime. So this is the probability of A prime, which means the probability of not A. If the probability of A is, let's say, 50%, then the probability of not A is also 50% because it's 1 minus the probability of A. If the probability of A is 20%, then the probability of the complement of A would then be 80%. Combined events, the probability of A union B. So a union works like an OR. So in this scenario, you can think of if I asked you to go to the cafeteria and bring me back a coffee or a muffin. If you came back with a coffee, I would be happy. If you came back with a muffin, I would be happy. If you came back with both, I'm still happy. When we find this probability, what we would have to do is find the probability of one event, so let's say the coffee, add it to the probability of the other event, let's say the muffin, and then you subtract out those intersections where they happen together, because otherwise the coffee and the muffins get counted twice. So we don't want anything counted twice. So we count each individual coffee, we count each individual muffin, and then we subtract out the number of times you brought me both. So it's that theory, but in probability concept. Mutually exclusive events are when I want a muffin or a coffee. Well, you can have both, so they're not mutually exclusive. Mutually exclusive is saying something like you want to play on the school football team or the school soccer team. The way sports work in New Jersey, you can't be on the football team and the soccer team at the same time because they're in the same season. So therefore, the probability of someone on the football team plus the probability of someone on the soccer team, there is no intersection to subtract out because those are mutually exclusive events. Independent events are if I have A and B, so I can take those two probabilities and I can multiply them together. So the probability of A intersect B would be the probability of A times the probability of B. So for example, if I am rolling a die and flipping a coin, those are considered independent because one doesn't have any impact on the other. So I would take the probability of, let's say, rolling a 3 on the die and the probability of flipping a head. And to get that combined probability, I would have to do multiplication here because it's an and situation, not an or situation. That's the difference. Conditional probability is the probability of A given B. So this little line here means given. Okay. So the probability of A given B, which means A happened after B already happened. So that probability is the probability of A and B, which we just discussed in independent events, divided by the probability of B. And we'll deal some more with that in a little bit. An experiment is an action having various outcomes that occur unpredictably, such as tossing a coin or rolling a die. A sample space is a set S such that each outcome of the experiment corresponds to exactly one element of S. For example, the sample space for tossing a coin has two elements. One is heads and one is tails. An event is any subset of the sample space. For example, either heads or tails. So the probability of an event, so P of the event, is the desired outcome divided by the sample space. And really, this should be the number of the desired outcomes divided by the number in the sample space. For example 1, suppose a die is rolled. give the sample space for this experiment, then find the probability of rolling a prime number. So the sample space we would list out as 1, 2, 3, 4, 5, 6. So when you're listing sample space, you just list it all out. Now, the probability of a prime number. A prime number is any number with exactly 2 factors. So that would be 2, 3, and 5. So that probability is 3 out of 6, which reduces to 1/2. I'm going to say something very important right now. Do not turn your probabilities into percents unless otherwise directed. Do not turn them into decimals unless otherwise directed. Just leave them as fractions. 3/6, 1 is 1/2. Leave it alone. Don't do anything else. Don't do more work. So the probability of 2 events. So the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. This is kind of what I was talking about before with the coffee situation. Find the probability of rolling a number divisible by 2 or a number divisible by 3. So the probability, so we're still talking about rolling the die. So the numbers on our dice are 1, 2, 3, 4, 5, 6. To be divisible by 2, it's going to be 2, 4, or 6. So that probability is 3 out of 6, which would reduce down to 1/2. The probability that a number is divisible by 3, well, that would be 3 and 6. So that would be 2/6, which reduces to 1/3. The probability of being divisible by both is just the 6. So that's 1/6, which doesn't reduce. So to find the probability of it being divisible by 2 or 3, we take the probability it's divisible by 2, add in the probability it's divisible by 3, and then subtract when it's both. So that will give us 4/6, which is 2/3. And if you look up here, it is 1, 2, 3, 4 out of 6. So this is a nice example to show you how it works. If there's no overlap, we discussed that. That would be like playing football and playing soccer. You can't do both in the same season. Conditional probability is the probability of an event A is the probability that the event will occur given the knowledge that B has occurred. This probability is written as the probability of A given B and read as the probability of A given B. If the events are independent, the probability can be found using the probability of A and B is the probability of A times the probability of B. So if they're independent, it doesn't matter that B happened. The probabilities stay the same, so we can just multiply them together. 2 yellow balls and 3 green balls are placed in a jar. One ball is randomly chosen, its color noted, and the ball is put back in the jar. This procedure is repeated for the second ball. Are these events independent? Why? As you think about this, the important thing is the ball is put back in the jar. So since the ball is put back in the jar, they are independent. So yes, because the ball is replaced between trials, the sample space does not change. So now we're going to find each probability. The probability that both are yellow. So the first one being yellow would be a probability of 2/5. The second one being yellow would also be 2/5 since we put it back in the jar. So that would give us a total probability of 4/25. The probability that they're both green. Well, that would be 3/5 times 3/5, which would be 9/25. The probability that they're the same color, well, that's both yellow or both green. So that would be 4 out of 25 plus 9 out of 25, which gives us 13 out of 25. The probability of a yellow then a green. So yellow is 2/5. Green is 3/5. So that would give us 6/25. Green then yellow is also 6/25 because multiplication is commutative. So when I change the order, it doesn't matter. It's still 6/25. This is a tricky one. The probability of each color, it doesn't specifically say which order it can be done in. So we're going to take the 6/25 from yellow first, add it to the 6/25 from green first, and get 12/25. The other way to do this is to take one of these. So let's say the probability of yellow then green would be 2/5 times 3/5. And then we multiply that by 2 to get the 12/25 that way. So there's more than one way to get these answers correctly. 2 yellow balls and 3 green balls are placed in a jar. One ball is randomly chosen, its color noted, and the ball is not put back in the jar. This procedure is repeated for the second ball. Are these events independent? Why? As you take a minute to think about this, the ball is not put back in the jar. So because the ball is not put back in the jar, the sample space changes. So no, because the ball is not returned between trials, the sample space changes. And you can even add in there the sample space changes for each trial. So this time, the probability that both are yellow, the probability that the first one is yellow is 2/5. But now I've taken out a yellow, so there's only one yellow left out of 4 altogether, which gives us an answer of 1/10. Both green would be 3/5 the first time. Now we assume we got the green the first time, so then that would leave us 2/4, which is 3/10. The probability that they're the same color, well, that's 1/10 plus 3/10, which is 4/10, which reduces to 2/5. Once again, notice I am not taking out a calculator. I am not turning these into decimals. I am not turning them into percents. I'm leaving them as fractions. The probability of yellow then green. So yellow would be 2/5. Now we assume that we took out a yellow, so there's 3 greens left out of 4 altogether, which gives us 3/10. Apparently, I forgot to leave myself space here. The probability of a green, then a yellow. Well, this is going to be the same probability again because switching the order of the numerators does not change the value once we multiply because of the commutative property of multiplication. So this one is again 3/10. And then lastly, one of each color would be 3/10. And we could do 3/10 plus 3/10, or we could do 3/10 times 2, which will give us 3/5. Each student in a class of 30 studies one foreign language and one science. The students' choices are shown in the table below. So we have chemistry, physics, biology, and French and Spanish. Find the probability that a randomly chosen student studies chemistry. Well, if we look, the total number of students studying chemistry is 8 out of the total number of students, which is 30, which reduces to 4 out of 15. Find the probability that a randomly chosen student studies chemistry given that the student studies French. So this is that given that we talked about at the beginning. So the denominator, given that the student studies French, is going to be the probability of French. The numerator is that the probability that they do French and chemistry. So the probability of French and chemistry is 7 out of 30, divided by the total number of French, which is 14 out of 30. When we divide these, we multiply by the reciprocal, which gives us 7 out of 14, which is 1/2. Now, you'll notice these denominators are the same, so they cancel out. So when you're using a chart, you can shortcut this a little bit and just take the number of French and chemistry and divide that by the number of French, because the denominators will cancel because you have the same number of total students. Are the events student studies chemistry and student studies French independent? Well, if they're independent, then the probability of A given B should equal the probability of A. Because if they're independent, it doesn't matter if it's given we study the French. Okay, so we just did the conditional probability, and we found the conditional probability is 1/2. So that was the probability that they studied chemistry, the probability of chemistry given French. So with this logic, that means that the probability they study chemistry should be 1/2. But if we look, the probability that they studied chemistry was 4/15. These do not equal each other, which means they are not independent. So we would write a little sentence: because 1/2 does not equal 4/15, the events are not independent. Given a student studies biology, find the probability they also study that should be Spanish, not Spandish, Spanish. So I would like you to pause the video, try this one on your own, and then come back and see if you got the correct answer. The probability of Spanish given bio is the probability of Spanish and bio divided by the probability of just bio. The probability of Spanish and bio is 9 out of 30. The probability of just bio is 12 out of 30. Simplifying this gives me 9 out of 12, which is 3/4. So that's it for the notes for today. The next page is your homework. The answers to these homework problems are posted on PowerSchool Learning. So you can do it and then check your answers there. If you have any questions, just like before, please work on these with your groups in class. And then if you have any questions, either send me an email or just pop in before school. I'll be here in the mornings. Have a great day.